My Earth Science Faithful, video number 1 of unit number 9, the last one. The universe. Astronomy notes. Here's the basics. Ready? Age of the universe. It's 10 to 20 billion years old. That is a long, long time. Video. See how this works. I'm going to mute me and show you a little bit about this Big Bang Theory.
Almost all astronomers agree on the theory of the Big Bang, that the entire universe is spreading apart, with distant galaxies speeding away from us in all directions. Run the clock backwards to 13.8 billion years ago, and everything in the cosmos started out as a single point in space. In an instant, everything expanded outward from that location, forming the energy, atoms, and eventually the stars and galaxies we see today. But to call this concept merely a theory is to misjudge the overwhelming amount of evidence. There are separate lines of evidence, each of which independently points towards this as the origin story for our universe. The first came with the amazing discovery that almost all galaxies are moving away from us. In 1912, Vesto Slipher calculated the speed and direction of spiral nebulae by measuring the change in the wavelengths of light coming from them. He realized that most of them were moving away from us. We now know these objects are galaxies, but a century ago, astronomers thought these vast collections of stars might actually be within the Milky Way. In 1924, Edwin Hubble figured out that these galaxies are actually outside the Milky Way. He observed a special type of variable star that has a direct relationship between its energy output and the time it takes to pulse in brightness. By finding these variable stars in other galaxies, he was able to calculate how far away they were. Hubble discovered that all these galaxies are outside our own Milky Way, millions of light years away. And so if these galaxies are far, far away and moving quickly away from us, this suggests that the entire universe must have been located in a single point billions of years ago. The second line of evidence came from the abundance of elements we see around us. In the earliest moments after the Big Bang, there was nothing more than hydrogen compressed into a tiny volume with crazy heat and pressure. The entire universe was acting like the core of a star, fusing hydrogen into helium and other elements. This is known as Big Bang nucleosynthesis. As astronomers look out into the universe and measure the ratios of hydrogen, helium, and other trace elements, they exactly match what you would expect to find if the entire universe was once a really big star. Line of evidence number 3, the cosmic microwave background radiation. In the 1960s, Arno Penzias and Robert Wilson were experimenting with a 6-meter radio telescope and discovered a background radio emission that was coming from every direction in the sky, day or night. From what they could tell, the entire sky measured a few degrees above absolute zero. Theories predicted that after a Big Bang, there would have been a tremendous release of radiation. And now, billions of years later, this radiation would be moving away so fast from us that the wavelength of the radiation would have been shifted from the visible light to the microwave background radiation we see today. The final line of evidence is the formation of galaxies and the large-scale structure of the cosmos. About 10,000 years after the Big Bang, the universe cooled to the point that the gravitational attraction of matter was the dominant form of energy density in the universe. This mass was able to collect together into the first stars, galaxies, and eventually the large-scale structures we see across the universe today. These are known as the 4 pillars of the Big Bang Theory, 4 independent lines of evidence that build up one of the most influential and well-supported theories in all of cosmology. But there are more lines of evidence. There are fluctuations in the cosmic microwave background radiation. We don't see any stars older than 13.8 billion years. The discoveries of dark matter and dark energy, along with how the light curves from distant supernovae. So, even though it's a theory, we should regard it in the same way that we regard gravity, evolution, and general relativity. We have a pretty good idea of what's going on, and we've come up with a good way to understand and explain it. As time progresses, we'll come up with more inventive experiments to throw at. We'll refine our understanding and the theory that goes along with it. And most importantly, we can have confidence when talking about what we know about the early stages of our magnificent universe and why we understand it to be true. Thanks for watching. Now make sure you click subscribe on our YouTube.
These guys go hard.
Sorry, that one didn't go from one slide to the other as easily as I like, but he had a lot of great information in there, and as a physicist, he's going to explain it much better than I would. There's another claim that it sounded like a big hum. So a lot of guys were listening to, when I say a lot of guys, the scientists were listening to the universe, and they rationalized that this hum is this leftover sound. So notes under Big Bang Theory for you to write. He talked about the proof. We're going to get to those in the notes, so you didn't have to have gotten it from the video. But that video, he did a good job of explaining those things. So underneath the Big Bang Theory part of your notes, you can start as the universe started as a single point. It was extremely dense, that point. It became unstable and exploded outward. And today the universe continues to expand. Because there's nothing in space that's going to stop that once that motion is set. Right? Now, proof. Evidence of the Big Bang. Some good things going on here. Light from distant galaxies all shift towards red. You have to watch this little infogram that shows up. It's going to change and explain this to you. So the star is moving away. The light becomes stretched out and red. If it was moving towards us, well, here's the fixed position. And then moving towards us. This is part of the Doppler effect. And the video for the Doppler effect is really going to explain the Doppler effect very good. So this red shift, they call it. Moving away, the light shifts towards the red side of the spectrum. Okay? So blue shift, unshifted, and red shifted. The red shift means I'm going away, and the blue shift means I'm going towards. So this is just understanding of what's going on all under number one, that we see a red shift. That's proof that the universe is constantly expanding outwards. That's why they think it started at the single point, because that's the only way to prove that it was going out continuously, is that it had to have an origin as a single point. Now this quick video is going to be shorter than that one, but this really, really explains what's going on. So let's pay close attention to the Doppler effect. That's going to be number 2. So the change in frequency of electromagnetic energy between the observer and the wave source. This is the written definition of the Doppler effect. You should write that down, and then we're going to see it now so you can understand it. Ready? Here we go.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency. And if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Cool. Good stuff, right? So Doppler effect. And then this last piece of evidence is the cosmic background radiation. Okay, good. All right, so that was a lot to put down for the one video. I'm going to check on this diagram and see. I see some rectangles and a circle and an ellipse. I don't know what the rectangle is with the soft edges is called, but I can definitely see a rectangle and an ellipse and a circle. Okay, so enough for this notes. Let's get ready for the next notes and get moving through astronomy.